In this video lecture, I will be talking about the very basics of matter, energy, and atoms and how they are important in human anatomy. We will talk about the structure of atoms, how the structure is different in different elements. Of course, the structure of an atom also reflects its function or behavior. Human anatomy and physiology, in addition to all of biology and all life on Earth, is subjected to the same laws of chemistry and physics as the rest of the matter in the universe. The same basic chemical and physical rules that govern how a bunch of rocks behave also govern how the atoms and the molecules in living things work. In other words, you can think of life as just very complex organic chemistry. In order to understand how the organs, tissues, and cells in our bodies work, we need to understand how the molecules and atoms in these cells work and what they're made out of. So we will cover the basics of what these things are made of at the finest level of detail. All substances in the universe, including our bodies, are made up of matter. When this matter is put into motion, we are talking about energy. So, if all the substances in the universe are made of matter, it's important to know what the matter looks like at the finest level of detail. For the purposes of human anatomy, this level of detail is the atom. Different types of atoms are known as elements. Elements and matter can exist in different phases: solids, liquids, and gases. Certain elements and molecules are normally found in one or more of these phases, and they can change between phases while remaining the same element. In other words, these phases differ in how the atoms in the matter move relative to each other. This movement of atoms and interactions between different atoms requires energy. There are broadly two different types of energy. Kinetic energy, shown on the right, is the energy to describe the movement of atoms and matter. This is matter in motion. The faster something is moving, the more kinetic energy it has. Potential energy is just that. It is the potential, or it is stored energy, that represents the potential to do work and move matter. In this example, the ball at the top of the hill, on the left, has potential energy. If pushed, it will gain speed due to gravity. Note that when the ball reaches the bottom of the hill, it will have no more potential energy. In other words, pushing this ball down the hill converts the potential energy into kinetic energy. Energy can neither be created or destroyed, simply transformed from one form to another. Remember, potential energy is the ability to do work and move matter. This can be stored in a number of different forms. We will mostly focus on the potential energy stored in chemical bonds. This energy can be converted to kinetic energy or to other forms of potential energy. During virtually all conversions or transformations, the transfer of energy is not 100%. Some energy is usually lost as heat, which is a type of random kinetic energy. Let's review this concept using the example of an archer drawing and firing an arrow. We can see here energy in several different forms. You might also notice that during some of these energy transformations, heat is released. Remember that heat is just kinetic energy that is not directed somewhere. It is the random motion of molecules. So what occurs when an archer draws and fires an arrow? They move their muscles to draw the bow back, and then they release the arrow, which then flies towards the target. The energy involved in this action starts even before you move your muscles. After all, you need some sort of source of energy in order to make the muscle movements. The food we eat is made of molecules with chemical bonds. These bonds represent potential energy, which our skeletal muscles can use and convert into kinetic energy to move our arms. Some heat is lost during this transformation step. The kinetic energy of our arm movement is then transferred into the potential energy of the bow, in the form of the tension in the bow when the arrow is fully drawn. Releasing the tension and firing the arrow transfers the potential energy in the bow into kinetic energy of the arrow, propelling the arrow into the air. This energy is further transferred and converted into heat in the form of friction against the air as the arrow travels towards the target. The car engine is another example. The gasoline that our car burns for fuel is full of chemical energy. This is the energy stored in carbon-hydrogen bonds in gasoline molecules. Breaking the bonds between these atoms releases heat energy and motion in the chamber, and this explosive motion moves the piston. This motion has been directed into the mechanical or to the kinetic energy of car movement. Notice again that some energy is lost as heat. Energy is not really lost or destroyed, simply transferred into unproductive heat. If you ever opened the hood of a car while the engine was running or just after you turned off the engine, you may notice the heat emanating from the engine. So far we have covered how energy is converted. It is never destroyed, only sometimes released as random kinetic energy or the random motion of molecules. This random type of energy or disorder is sometimes referred to as entropy. Again, entropy is a measure of disorder or randomness in a system. The first law of thermodynamics is that energy is never created or destroyed. The second law is that entropy always increases. You could think of it in the following way: that random kinetic energy is the default or preferred type of energy in the universe. The universe will spontaneously become more disordered, and to reverse this trend and to create order requires an input of energy from somewhere. This sounds abstract, but there is a simple analogy, a simple everyday example that you are probably familiar with. Through normal everyday activity, your bedroom would become a mess if it is not regularly cleaned. This is the natural order of things, where a messy, random room is the default. This is the increase in entropy. It will happen without any extra energy to organize it. Again, to reverse this trend, extra effort is required. When discussing the energy in atoms and molecules and talking about chemical reactions, it is important to remember that molecules with many bonds represent a large amount of potential energy, which can be transferred in a downhill fashion to kinetic energy, sometimes for a certain purpose, or sometimes just as random movement of molecules or heat energy. You should remember that the natural transition is from order or potential energy to disorder, not the reverse. When we talk about matter, the finest level of detail we can discuss it, outside of some branches of physics, is that of the atom. Atoms are made of electrons, protons, and neutrons. The number of these components each atom has, or in other words its structure, will determine how an atom behaves. Atoms with different numbers of protons are considered separate elements, and they are referred to by name. Atoms have a dense nucleus, which contains the protons and neutrons. Protons are particles with a mass and a positive charge, while neutrons are uncharged. The positive charge of the protons attracts electrons, which are small particles of almost no mass, which have a matching negative charge. That is to say, the charge of one proton is attracted to and balanced out by the charge of one electron. We can see this in action with a typical atom. The element helium is depicted here. However you represent it, the protons and neutrons are in the middle of the atom, or the nucleus, and they are orbited by the electrons. The electrons try to get as close to the positive charge of the proton as they can without crowding each other out. We have names for atoms with different numbers of protons. These are the different elements, like hydrogen, carbon, and oxygen. Each of these elements have a certain number of protons, also known as their atomic number. As we saw before, atoms are made from protons, electrons, and neutrons. The protons and neutrons, which are found in the nucleus, are the particles in the atom that have mass. So the total mass of an atom, or its atomic mass, is simply the number of protons and neutrons in the atom. The different elements can be arranged in a repeating table, known as the periodic table of elements. This arrangement matches the size and behavior of the atoms, as we will see throughout the rest of this video. Here, I'm only showing the first few rows of the table, since these contain the elements most important for human anatomy. Before I talk about how these atoms behave, just one more note about the nucleus of the atom. Atoms with different numbers of protons are different elements. Atoms with the same number of protons are of the same element, and atoms of the same element that have different numbers of neutrons are called isotopes. For example, hydrogen normally has one proton and no neutrons. An atom with one proton and one neutron is an isotope of hydrogen. For the most part, isotopes behave the same as the normal version of the element. In fact, the behavior of an atom or an element is largely dependent on how many electrons it has and how those electrons are arranged. Negatively charged electrons are attracted to the positively charged protons in the nucleus. An atom with two protons, like the element helium, has the ability to attract two electrons, which are shown in orbit as gray spheres. The electrons are attracted to the positively charged protons in the center of the atom, and they try and get as close to the center as possible. However, there's only so much room available, so the more electrons there are, the further out some of them must orbit. These orbits fall into different energy levels. The first energy level is the electron equivalent of front row seats. There is one orbital in this energy level, and it has space enough for two electrons. As we will talk about, each orbital has room for two electrons only. If our atom has more than two protons, it can attract more than two electrons. However, these additional electrons cannot fit into this first energy level. It would be too crowded. They must fit into the second energy level, which has 4 orbitals. The reason why different energy levels have a different number of orbitals is beyond the scope of this video. However, you should remember the following: that each orbital has enough room for 2 electrons, and that the first energy level has 1 orbital, while the second energy level has 4 orbitals. To help you remember, think of the following analogy. The energy levels and orbitals are a bit like seats at a concert, a sporting event, or a movie theater. The first energy level only has 2 spots for electrons. These are like front row seats. The second energy level, or the second row, has additional space. As we will see in a moment, electrons like to get as close as they can to the nucleus without getting in each other's way. Just like people sitting at the movies that avoid sitting next to each other if there are empty seats nearby, all orbitals fill up with 1 electron before any of them fill up with 2. We will return to this point in a moment. The elements in the periodic table we saw before are actually arranged according to their energy levels and orbitals. Each row features atoms with more and more protons, which also have more electrons and thus more energy levels. Elements in the leftmost column have an outer shell or outer energy level, also called the valence shell or energy level, that only has 1 electron in it. Elements in the rightmost column have completely filled valence shells, and the elements between these 2 side columns have partially filled valence shells. Remember, all orbitals for a certain energy level must have 1 electron before any of those orbitals can have 2. Think about the following analogy. A small house or apartment can house, let's say, 2 people. This is equivalent to our first energy level. If more people need a place to stay, the only next available housing option is a building with 4 rooms or 4 apartments. So again, these 2 buildings correspond to the first 2 energy levels, and each apartment or room is an orbital. Let's say that we have 5 electrons that need to be put in the second energy level. This is the case with the element nitrogen, for example. Just like an apartment building, people would prefer to spread out rather than to cram 3, for example, into a tiny apartment. In the case of a building, the landlord would also prefer to have 1 person in each room before any had 2, so that there are no unfilled rooms. As we will see, there is also a preference to have all of the rooms filled with 2 people. In this case, there is enough room for 3 more people. In other words, this energy level has 1 filled orbital and 3 partially filled orbitals. As I had mentioned, just as the landlord might prefer to have 2 people in a room, maybe because they could afford to pay a higher rent that way, and they would also prefer to have all of the room filled, so too do atoms prefer to have all of their orbitals for a particular energy level filled. Atoms that have filled valence energy levels are stable, while atoms that have partially filled or empty orbitals in their valence energy level are reactive. These atoms are reactive because they want to either fill these empty spots or get rid of the entire partially filled energy level. In either case, the result of that action would be an outer or a valence shell that is full. To do this, and to achieve the goal of a filled valence energy shell, atoms will either steal or donate electrons from other atoms, or 2 atoms might pool their resources and share a pair of electrons. Atoms that participate in this behavior are forming chemical bonds with other atoms. These bonds bring some atoms together to form larger molecules. When one atom donates electrons to another, or when it steals electrons, it will end up with a different number of electrons compared to protons. Such atoms are called ions, and they have a net positive or negative charge. Atoms with more protons than electrons will be positively charged, and they are known as cations. Atoms with less protons than electrons will be negative, and they are known as anions. One example of a cation is when a sodium ion donates an electron to another atom. The resulting sodium atom has one extra positive charge unit that is not balanced by an electron. The sodium atom would also happen to have a stable valence shell of electrons. It's important to remember that the chemical behavior of an atom depends upon the arrangement of its electrons. In other words, the number of electrons it has and the number it needs to either donate, steal, or share to have a filled valence shell will dictate how it will interact with other atoms. In biology, we need to only worry about these details for a handful of atoms. In fact, the vast majority of our body mass is made of only 4 different elements: carbon, oxygen, nitrogen, and hydrogen. Knowing a few things about each of these elements will be very helpful if you continue to study organic chemistry or biochemistry. For example, carbon has 6 electrons to match its 6 protons. 2 electrons completely fill its first or inner energy level, and the remaining 4 are found in its valence energy shell. In other words, the valence energy level of carbon has 4 partially filled orbitals, and carbon needs to share 4 more electrons with other atoms to form a stable molecule. You could take other elements from the periodic table and, following these same rules, determine how many more electrons it needs to form a stable molecule. If you do this, you will find that oxygen needs to form 2 bonds, or needs to share 2 electrons with other atoms to become stable. Nitrogen needs 3, and hydrogen needs 1. These numbers and the principles behind them govern a lot of the biochemistry that occurs in our body.